Hello, everybody. So I decided instead of making a video of half the lecture that we didn't get through in class, I'm just going to make a video of the entire lecture. I'll probably do it in two parts. That way you can skip to the second part if you already feel like you know everything from the first part. But I thought it'd be a good review for everybody just to have the first and the second part of the lecture, especially since this is the kind of the electronic properties and structures thing with like the wave function and all that quantum mechanics. It's a little bit complicated, so I figure it's better to just do it this way than having just half the lecture. So let's go ahead and get started. And I apologize if you hear noises in the background. My dogs are actually here sleeping, and they might bark, they might jingle their collars or something. So if you hear anything, that's what that is. Anyway, so let's go ahead and get started here. I'll go ahead and switch over to presentation view, and you should be able to see the presentation now. And then my mouse here to point, good. And then my pen too. Okay, so everything's good. Let's go ahead and get started then. So in this lecture, if you recall, even if you don't recall, we're going to talk a lot about the uh, waves and electromagnetic radiation. We're going to talk about quanta and what the photoelectric effect is, atomic emissions, spectra, and the Bohr model. We'll talk about Heisenberg uncertainty principle and its applications, or rather implications, and quantum mechanics. We'll talk about the quantum numbers and Lm sub L and then M sub S, which we talked about that at length in class, but I'm going to talk about them again just to make sure everybody's familiar with them. We'll talk about the different orbitals, S, P, D, and F, and what their shapes are. And then also we'll talk about the Pauli exclusion principle and Hund's rule. And then I'll teach you how to do the electron configurations and orbital diagrams, and also describe and explain periodic trends in the next video probably. So this one will be only the first part. We'll start with I'm not sure how far I'm going to go in this video. I might stop here for this first video, and then we'll go from here down for the last video, right? Or maybe that sounds about right. Yeah. So this will be where we end for this video, right? And then so this is going to be the first video, and this will be the second video. Cool. So let's go get started. So the first thing that we need to talk about when we talk about electronic structure is that what is electronic structure? Well, really, it's just the arrangement and the energy of the electrons, right? That's what we really care about here. The arrangement, meaning what orbitals they're in, and also how much energy they have. And as we go through this lecture, you'll see that it's not as simple as we used to think it is, right? And then we're also going to talk about waves, and if you recall from class, we talked about how electrons can be a particle in a wave, or light can be a particle in a wave, and how matter can be a particle in a wave. So we'll go through and discuss that again here. So what are waves? Well, the most common, to understand what the electronic structure of atoms is, you have to understand electromagnetic radiation, right? And what is electromagnetic radiation? Well, electromagnetic radiation comes in the form of all the light that we see and all the light that we don't see. So, for example, UV rays, X-rays, microwaves, infrared radio waves, gamma rays, and then probably the one that you're most familiar with, which is the visible spectrum, which is the colors of the rainbow, Roy G. Biv. So all that stuff, if you talk about, so you say white light, and how the sun projects white light to us on Earth. I know it looks kind of yellow, but it's white light coming from the sun, and all that light, right, is actually the combination of all the colors together, including the colors that you can't see, like the light that you can't see. So the visible spectrum is Roy G. Biv, right, where you can see the colors of red, orange, yellow, green, blue, indigo, and violet, right? And so you can see all those. So that's like the abbreviation everybody uses. It's Roy G. Biv, right? So red, orange, yellow, green, blue, indigo, and then violet. That's the colors of the rainbow, and it's also the colors of the visible spectrum. And then on either side of that visible spectrum, so you say to the right side, depends on what my camera is doing. So I think it's actually opposite on the video, but whatever. If you're going, say, violet and above, that then turns into UV and then X-rays and gamma rays, and we'll talk about that in more detail later. And then below red is infrared, right? And below that is uh, microwaves, and below that is then radio waves. And so that's the entire electromagnetic spectrum. And we are sure that the electromagnetic spectrum or radiation actually travels as waves through space, and it's a wave of light, right? That's coming from the sun to us on Earth, right? Or it could be not even from the sun; it could be from anywhere in space, right? Through and it hits us on Earth. And how fast are they going? They're going the speed of light, so very fast, right? Very, very fast. And we'll talk more about that in a second. So the most important thing about waves is their wavelength. That dictates the energy they have, the frequency they have, and everything else that you would care about for a wave. So let's talk about those now. And so a wavelength is essentially the distance between one peak of a wave and another peak of a wave, right? Some people also call a wavelength the distance between two valleys, right? Or some people call a wavelength the distance between the beginning of a wave and the end of a wave. So all of those can be wavelength because they're all the same distance, right? And so the symbol for wavelength is lambda, so that's what I'm drawing there, right? So that's lambda, okay? And that's a wavelength, okay? So then, now that you know what a wavelength is, what is a frequency? Well, a frequency is basically how many times you can have a complete wave within a second. So per second, basically, what it is. And so the unit of the unit of frequency is usually hertz, right? Or I think it's like Hz for short, right? But essentially, what this means, though, is that a hertz is cycles per second. So how many times can you see a wave, a complete wave, in 1 second? So if you look at this wave A here, the complete, I'm going to change colors real quick so I don't get confused here. And so, come on up, little color thing. That's okay, who cares? Right, so remember that a complete wave, right, is, I'm just going to erase some of this so I can draw it better because I can't really see what I'm doing here. A lot of colors. So let me erase some of this. I'll erase this one here. There we go. I'll go over to green now. Okay. So I'm going to draw another position for a complete wave, but a complete wave is a section of a wave that has both a up and a down, right? Or a peak and a valley. So that's a complete wave. And so if we imagine then that right here, we use black now. If we imagine that this is an x-axis, right, and this and the x-axis unit is time in seconds, right, and then this is 1 second right here, right, 1 second. Then the question is, right, what is the frequency? Well, for this one here, right, since we have, let me change the color one more time. Do purple now. Since we have 1 and then we have 2, right, complete waves, this frequency is 2 hertz. Or you could say 2 cycles per second, right? And so that's what the frequency is. I'm going to go away real quick so we can see the next one, the next picture here, right? Let me move my head out the way. There we go. If we look at this one now, again, let's just imagine that this is the x-axis here, and this is the time, right, in seconds. So, and this is 1 second right here. You can count up how many complete waves we have. 1, 2, 3, and then 4. So since we have 4 complete waves, then we know that this guy here is 4 hertz, or 4 cycles. I promise that's a cycles. There we go. Cycles per second. Right? 4 cycles per second. Saccade. Sorry, second. There we go. 4 cycles per second. And so that's the frequency of that wave. So I want you to notice that you don't have to actually count the entire wave, like, draw the entire wave to count it. It's actually just, you could also just count the number of humps. 4 humps means 4 complete waves, which means 4 cycles per second, or 4 hertz, right? Same up here, just count the humps. 1, 2 humps. That's 2 cycles per second, or 2 hertz, okay? So the thing I really want you to notice about this, though, is that notice that as the wavelength gets longer, like up here, the frequency gets smaller, right? The frequency gets smaller. So here we have a wavelength from here to here, right? And we only have 2 cycles. Okay, we only have 2 cycles. But then if we're here on our wavelength, the wavelength on this bottom one is actually half the size of the one at the top, right? And now we have 4 humps, right? So the relationship that you should know here, right, and we're going to say it multiple times, but as the wavelength goes up, right, the frequency, or they have it looking like a V here. That's actually the Greek letter naught, right? Sorry, not nu, the Greek letter nu, and so that's frequency. So as the wavelength goes up, the frequency goes down, right? And then the opposite is true too. As the wavelength goes down, right, the frequency goes up, right? So what that means to you in life is that the higher the I'm trying to make this clear here, so I'm going to erase that and do that again. There we go. Okay. Back to writing. So what that means to you is then the higher the wavelength, which is, remember, lambda, the higher the, oh, I messed that up, sorry. Let me see, let's see here, let me erase that one more time. Got a little bit ahead of myself here because I started running out of room. There we go. So the higher the wavelength, right, the lower the frequency. And that essentially means the lower the energy, right? So that's the big thing there, right? That's the big thing to know here. And then again, the opposite is true, right? And I'm going to erase my 2 cycles thing there so I can have some room to write. I might have spent a lot of time on this slide, and I'm sure we're going to talk about this in the next slides, but I just want to make sure we get that out there quickly, right? And so if that statement is true, then this statement is also true. The lower the wavelength, again that's lambda, right? The higher the frequency, again, that's not new. It's like a curvy little V, right? Which means the higher the energy. The higher the energy, right? So the higher the wavelength, the lower the frequency and the lower the energy. With the lower the wavelength, the higher the frequency and the higher the energy. Okay? Those are key points that you need to know right there. Very big points. Okay? So this is just kind of a little graph that shows you, or a little plot that shows you the relative energies of different electromagnetic spectrums and their wavelengths, right? And so, like I was saying before, here's the visible spectrum, which is actually a very small part of the of the entire electromagnetic radiation, right? Excuse me. But you can see from up here, right, as your wavelength increases, right here, your energy decreases, right? It's only when your wavelength is decreasing, if you go this way, right, then your energy is increasing, or your frequency is increasing, right? So they have what we call an inverse relationship. Right, so there is an inverse relationship between energy and wavelength, and there's also an inverse relationship between frequency and wavelength. Whereas for frequency and energy, they have a direct relationship, because when one goes up, the other goes up, right? So inverse means that when one goes up, the other goes down, whereas direct means that when one goes up, the other goes up. So the inverse relationship here, where one goes up and the other goes down, is going to be between wavelength and energy, or wavelength and frequency. On the other hand, if it is between energy and frequency, they have a direct relationship, because as one goes up, the other goes up. As one goes down, the other goes down, right? So you can just see that too from this little visualization here. We have very, very short wavelengths right there, so they're very high energy, whereas we have very long wavelengths here, so they're very, very low energy, right? So what are some of the things that you know? Let's go towards the right first. The next one after visual spectrum is infrared, and we all know infrared because all of our remote controls work on infrared. In fact, I may be able to. Do I have an infrared remote somewhere here? Maybe. Maybe. Okay, so I have a Roku remote here, so I'm gonna switch over to my camera view, headshot view, and let's see if this does anything. There you go. You see that? I just turned on my Roku TV, as you saw. That's behind me. But as I press the button, you see the little light coming on right there inside my remote. That is an infrared light, right? If you were to look at this, you couldn't see it because your eyes wouldn't be able to register the infrared light. But a camera can definitely register an infrared light. You can see that. Oh, there we go. Look at focus. Thank God. Focus. Let me cover my face, maybe. There you go. There you go. So that's infrared light coming from your remote control. Also, we use infrared light for night vision too. Let me switch back to presentation view. All right, for night vision. The next one after that is microwaves. Microwaves is all around your life, and microwaves is what your cell phone runs on. It's what your Wi-Fi runs on. It's also how we get weather maps, right? It's also probably the last thing I talk about. That's probably the most important, is that it's a microwave. You can cook your food with microwaves, right? And then the last one is radio waves. All right. Ever notice why? Do you ever notice that when you listen to the radio in the car, if you still do that kind of thing, you can like almost be completely outside the city, 100 miles away from like Dallas, you can still hear the radio station. And the reason why that is because the wavelengths are so long, they travel far. They travel really far. And then on the other side, we have UV. I guess the most benign thing about UV is that you can use it for curing your dental implants, right? But really, UV is most prevalent when we're talking about sunlight and getting skin cancer, because UV light can actually change the DNA in your skin and give you skin cancer. And so that's interesting. Then after that, we have X-rays right there. So X-rays are pretty strong too. They go straight through your skin. They can see your bones. That's why we use X-rays, except they're very dangerous. That's why when you get an X-ray, the X-ray techs have to like wear lead vest. So that's what X-rays are. And then we have gamma rays, and gamma rays are probably the strongest electromagnetic rays, and so those come from the sun or the cosmos, and then we use gamma rays to do like PET scans and stuff like that, right? So one of the things I might ask you to do in this unit that is calculation wise, and let me change my thing real quick here so you can see, is determine either the, remember that this is the wavelength right here for lambda, and then this is the frequency for nu, and then the new one here is actually c. That's the speed of light. And as you can see right here, we have the speed of light at 3.00 times 10 to the 10 to the 8th meters per second. So light travels pretty fast, which makes sense because when you turn on the light switch, the light just fills the room immediately, right? Well, it's just going so fast that you think it's happening instantaneously, but it definitely is going at a certain speed, and that is 3.00 times 10 to the 8th meters per second. So I may give you, knowing that this is a constant right here, right? I might give you a wavelength, and you would have to solve for the frequency. Or if I give you a frequency, you would have to solve for the wavelength, right? And so the thing to note about this is that there's a joke I like to say, and the joke is, what's new? And then the response is C over lambda. So just remember that, okay? What's new? C over lambda. What's new? C over lambda. What's new? C over lambda. So you always know what the formula is for determining either the frequency or the wavelength, okay? All right, so this is just a kind of a table that shows you the scale, right? A radio wave can be on the order of kilometers. I mean, that's really long, right? And then radio waves are, yeah, so meters to kilometers big. Microwaves, centimeters to millimeters, so they're much smaller, right? Much smaller than radio waves. But then we get to things like the infrared, which is 1 micrometer. Ultraviolet's nanometers, right? I always tell people my favorite color is 450 nanometers because that's blue, but even ultraviolet's even lower than that. That's like 300 to something, 300 and below for ultraviolet nanometers. And then once you get down to the X-ray and the gamma rays, those wavelengths are so small, you're at the angstrom level, right? So that's really small. So then the question is this: why are electronic properties not explained by waves? Right. Well, one of the things that happens is we have this thing called black body radiation, and black body radiation is when you it's actually on the next slide. So I'll just go to the next slide real quick. When you heat something up, it glows, right? But where the heck does that color come from? Where's that light come from? Who the hell knows, right? And so electromagnetic radiation is not the responsible for the light that you see when you heat something up and it glows, right? So the waves, the electromagnetic waves, definitely don't do that. So that's one thing that the wave explanation for things doesn't account for. What are some other things? Doesn't account for the photoelectric effect, which we talked about before. That's like the basis for your solar panels and stuff. This is actually how Einstein won the Nobel Prize. So yeah. And then the other thing that waves don't really explain is emission spectra. And emission spectra is what I showed you in class with that Tesla coil, and we ran like electricity through the gases, and they all shown up different colors of light. That's the emission spectra. And waves don't explain that either because there's no electromagnetic radiation coming from the atom, right? That we're the gas atom, right? So it has to come from somewhere. Where is it coming from, right? And so it doesn't explain that either. So back in the day, we used to think that energy was something that was like what we call continuous, where you could just keep on walking up this kind of like this inclined plane, and as you walked up, you just increased, and got more energy. Very uniform kind of thing. Well, Max Planck actually explained that in fact it's not like that. It's actually what we call quanta, where we have quanta is another way of saying discrete energy levels. Discrete energy levels. That means more like going up the stairs, because the stairs are all at different levels, right? And you can't step between the stairs. You can only step on the next stair or the one below it. And that's what we think energy is, especially in electrons, right? And so we can call that quanta. Quanta. It's actually where the word quantum mechanics come from, though. You know, the smart thing people always talk about quantum mechanics. But yeah, that's where that word comes from. Okay. And so, talking about that now, let's move on to talking a little bit about Einstein. Um, so I told you Einstein came up with the photoelectric effect, and this is actually how he won the Nobel Prize. And so from this, he was able to deduce this equation, which is energy right here. The E there is energy, and then the H here is called Planck's constant. And then this is the same V or nu that we had before, which is the frequency. So you might be asking yourself, why do I need another, equation here? Well, this equation right here actually relates nu, right, which is the frequency, to energy. Because on the previous one where I said, remember this equation right here. I'm sorry, I blocked it out, but I'll write over here, right? What's nu? All right, it's C over lambda. Well, this equation only tells you what the frequency is the wavelength is of a piece of electromagnetic radiation, and then this one, it only tells you what the frequency is. It doesn't tell you actual energy. So how do you convert either the frequency or nu, or lambda, which is the wavelength, into energy? Well, you use this equation right here, right? And you plug in. So one of the questions I might ask you is, I might say something like, I might say, you have, this electromagnetic radiation is 450 nanometers, right? Determine its energy, right? So how would you do that? Well, first thing you say is, what's nu? And so that's C over lambda, right? Like that. And so I just told you that the question is, what is the energy of electromagnetic radiation, we're just going to say EMR for short, at 450 nanometers. I don't know why I put 450 degrees there, sorry. I was writing too fast, that's what that was. Writing too fast. Let me erase that real quick so I don't get confused. There we go. At 450 nanometers, okay? And so all you really have to do is take the 450 nanometers and plug it in for lambda, right? And then for the speed of light, which is what we talked about in the previous slide, that was 3.00 times 10 to the 8 meters per second. Plug it in, put that in there, and then you get the V, or the frequency, right? You'll solve for the frequency. And then once you solve for the frequency, you can plug the frequency in over here for that nu, right? This is Planck's constant right here. So you'll just plug that in for Planck's constant right there. And then now all you do is multiply the two numbers, right? Whatever frequency you got times the 6.26 times 10 to the negative 34th joule seconds. And then that's how you solve for the energy, okay? So just to be clear, I will ask you to do this. So, just the thing to remember is what's nu? C over lambda, okay? So we did this in class, how I was able to run electricity through some glass that had gases in them, and they were all different colors. And they're all different colors because each atom has a different emission spectra. And most have multiple colors that will show, but when you do it just without a spectrometer or a prism, all you see is one color, right? That's actually the combination of all those lines, all those spectral lines. But in general, when you look at an emission spectrum, you see multiple lines. So, for example, hydrogen, which I did run, remember, I did run some electricity through the hydrogen gas for you to see, and it was kind of like purplish colored. Remember that? Well, that's because hydrogen's emission lines are right there, which is purple and purple, right? A slightly lighter purple, and then like a kind of a teal blue right there, and a little bit of red. And so when you mix all those colors together, you see the purplish red color that you saw when I ran electricity through the hydrogen ampule, right? And then this is even more apparent. So here's neon. Does anybody remember the color neon glowed? Yeah? No? Well, neon glowed orange, very bright orange. Remember that? And so the reason why that is because when you mix all these lines up together for neon, really most of it is in the yellows and the reds, right? And that's why you get that's why you get the orange color when you run electricity through neon, right? And get the neon lights. So these are called line spectrums, right? And so line spectrums are different for every atom, okay? And even though when we ran electricity through it, we only saw the the combined of all those wavelengths lines that we're showing, you can yourself see the lines if you were to just to have that light going through a prism, and the prism will split up all the colors, and you'll see the exact colors that you see here for hydrogen and neon or any other gas that we try to put into that thing. I think my favorite was krypton was probably my favorite, right? So contrast that with a continuous spectrum. Continuous spectrum is you see a whole like gradient of colors, right? That's a continuous spectrum. Whereas a line spectrum, all you see is lines, right? So that's the difference there. So we talked a little bit already about the hydrogen spectrum right here, right? It's like that purple color, that light lavender color, some teal, blue, green there, and some red, right? Excuse me. I woke up really early this morning, 6 o'clock actually. Anyway, and so we can actually determine what these colors are gonna be by using this thing called the Rydberg equation, right? And from Johannes Rydberg. But I'm not going to make you do that. I just want you to know that it exists, right? But it's because of this equation right here that the colors of the line spectra, right? The colors of the line spectra of stop writing. All right, the colors of the line spectra match up to the energy levels of the Bohr model of the atom, right? And so I'm not going to make you calculate anything with the Rydberg equation, but just know that that exists, and that's how we were able to get the the energy levels of the Bohr model, right? And so, and that's the next question, right? Our next slide, right? The Bohr model. If you remember, right, the Bohr model started out with. I'm just going to use hydrogen as an example. And so it had hydrogen has one proton in there, and then its innermost energy level has got one electron. That's a hydrogen atom, right? And so, and then if we're a bigger atom, it'd have another energy level here, another energy level here. Okay, I kind of did that bad there because it should be a perfect circle. I'm doing my best, right? I'm doing my best. I'll try that again. Let me try that again. It's really this one that kind of looks funky. Okay, and then purple again. Purple. There we are. All right, and so remember this is it was better than before. Anyway, so remember this is what the Bohr model looks like. He proposed that the nucleus was centered that held protons and neutrons, and then we had the electrons. They resided in different energy levels outside the nucleus, and so one of the things to note here is that the ground state, or the very first energy level, which is the one that hydrogen has open or has occupied, that's called the ground state. Right. Well, I mean, it's called the ground state because that's the one that hydrogen has as the ground state, right? But it really depends on what level the electron originally came from, because this ground state right here is also known as n equals 1, right? And that's the principal quantum number. We'll talk about that in a second. But as you move out and get to the second ring right here, or second orbit, that's n equals 2. and the third orbit is n equals 3. And we'll talk again. We'll talk about that in a minute when we get to the Bohr model, not the Bohr model, the principal quantum numbers and such. Right. So what happens is that when you pump electricity into an atom, right, it will promote one of its electrons, right, from the ground state up to a higher energy level, right, and that's what we call excited. Once it gets up here, that's called an excited state. All right, so I even wrote it there. I didn't know I wrote it there, but I wrote it there too. All right, but then every time you have an electron go up in energy, right, it has to come back down again. And when it comes back down, it releases light, and that's why we get the color, because the energy has to go somewhere, and so that's where we get the color from the when we run electricity through those gases, right? So yeah. And so this is just reiterating what I just said about the Bohr model, right? Each one of these right here, this n equals 1, n equals 2, n equals 3, n equals 4, those represent the actual energy orbitals, right? Those are the electron orbitals. Orbitals that are around the atom, and those are where the electrons reside. And so, the smaller the atom, the fewer the electrons, and so they'll slowly start to build up, right? And so n equals 1, of course, is the ground state or the first energy level. And then the second energy level is n equals 2, third is n equals 3, and then fourth is n equals 4, right? And so when we have it so that there's these orbitals right here that are at certain energy levels, right? We call that allowed energy state, right? When an electron gets promoted to a higher energy level and it's actually allowed to go there, right, and stay excited for a little while before it comes back down, that's called being in an allowed energy state. Because it's important to know, because there are some energy states that electrons are not allowed, right? So it's good to know. So whenever energy is absorbed, it's always emitted, like I said, right? And so in the case of our hydrogen gas and the Tesla coil, as we push energy in the form of electricity to excite those electrons in the hydrogen gas, they will go up to the higher energy level and then they will fall back down again. And as they fall back down, they release light, and that's why we see light. And that's just the Einstein equation again, which is energy equals Planck's constant times the nu, which is the frequency. Okay. And so, just some more talk about the ground state and the ground state and the excited state. Right. Again, electrons can get promoted to either that one there, 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 and then they also get demoted too, right, and come back down again, or they might even come all the way back down to the ground state. And so the thing to note there is that the electrons are getting promoted to allowed energy states, right? At the n equals 2, the n equals 3, and the n equals 4, n equals 5, right? Because those energies actually do exist. The point of this slide is to show you that an electron will not be promoted like halfway up, like between 2 and 3, like that. That would never happen, because there's really no such thing as a 3.5, n equals 3.5, right, or an orbit at that spot. So yeah, you'll see that electrons will get promoted only to available energy levels, and when they get relaxed, they'll release light, and they won't get relaxed just by falling down. They're going to have to go all the way back down to the ground state, right? All the way back down to the ground state, right? So I guess, oh yeah, so one of the things to note here is whenever you have a positive A change in energy, that means that we have energy being absorbed, right? So right here we have we're in the n equals 1 right there, right? And so this electron right here is getting promoted and it's absorbing energy. And so you're putting energy into the system, right? And so that means this is a positive change in energy, right? And so the change in energy is positive. There we go, right? And then whenever the electron releases or goes back down from the ground state, this is going to be a negative change in energy. Right, that's going to be a negative change in energy. And the reason why is because the energy is leaving the system, right? So now you're at a net loss, right? And you've lost it. You lost some energy. Okay. And so the thing to know about this is that the principal quantum number, that's the final principal quantum number of the absorption, will always be greater uh, than the initial one, right? And so the initial one here was n equals one, and as you can see, n equals two, which is the level that the electron got promoted to, is higher than n equals one, which is borne out by this statement right here. Okay, and that's I think that's basically it for that. Oh yeah, so and this one here is only for the absorption. When there's during the release or the emission, right here, it's going to be the opposite, right? Where the final one, right, which is this one right here, will be less than uh, the final one, right here. This will be less than the initial one, which is here, right? So two is less than one, and so it's true. That's true there. So the big thing there is, right, when energy is absorbed, you've got a positive change in energy, right, and then the final n will always be greater than the initial n. Whereas when you have a negative, what's happening there is you're releasing, right, some light or emission, okay, and when that happens, the final n will be always smaller than the initial n, right? And so the funny thing that, and I mentioned this in class already, is that we did all these calculations and we figured out all these wave functions and all this stuff, all these quantum mechanical things, and it turns out that all the math only works for the hydrogen atom. It's something we call like the particle in a box thing, where we can only really figure out what the position of an electron, like for a single electron system, which that system is hydrogen. So in all of chemistry, as we learn how to do and work with electrons and other atoms that are a lot more than hydrogen, all of our calculations and theoretical bases are based on hydrogen, regardless of the atom that we use. So we call them hydrogenic orbitals, right? Because they're all based on hydrogen. But that's the closest we can get, and there's research being done right now to figure out the rest of it, but it's very difficult research to do, and so yeah, we everything we teach you, even though it's about other atoms in this chapter, it's still going to be uh, based on hydrogen's numbers. It won't be based on the atom that you're actually looking at, right? Because no one's ever figured out those numbers yet, right? So yeah. And so here are a couple important things from the Bohr model, right? Electrons exist only in discrete energy levels. I showed you that already before. Those are the stair steps, right? And those stair steps, they're described by, or they're named by, their quantum numbers, right? Which is the n number. N equals 1 is that first orbital. N equals 2 is the second orbital. N equals 3 is the third one, and so on, right? Those are all the principal quantum numbers, and then they're also the energy levels that electrons can occupy, right? And so that's super helpful, right? And then energy is involved in the transition of electron from one level to another. Again, we said that where you have an electron at the ground state, you've got to put energy into the electron for it to get promoted to the next highest energy state, and then when it comes back down, right, the energy is released. So energy is involved, and the way energy is involved in the transition of an electron from the ground state to the n equals 1 state, or from the n equals 1 state back down to the ground state, there's either an absorption or a release of energy, right? So de Broglie is another person that's interesting too, because he was a part of this whole quantum mechanical revolution, and he described how matter can be used as waves too. And so this is actually a electron micrograph right here that shows the wave nature of light, right? The wave nature of light. But matter can be waves too, and some of the bigger things in our lives have very wide wavelengths that we don't even notice, but everything's made of waves, right? But the interesting thing here is that since de Broglie, really, he was more concerned with things in the macroscopic world and not the microscopic world. We're talking about things that we touch every day, not like at the atomic level. Um, he came up with another equation again that has nu in it, or not nu, lambda for wavelength, right? And then nu for frequency, and then Planck's constant. And then so, but the thing that's very interesting is that he actually has an m in there now. He added an m. He figured out the relationship between mass and the rest of these things, right? So if you have a mass of something and you have the wavelength of something, you can figure out its frequency more accurately than you'd be able to before, because now we take into account the mass of the object, right? So that takes me to talking about one of my personal heroes. His name is Werner Heisenberg. You may have heard of him before. He sold drugs in the show Breaking Bad. No, I'm just kidding. It wasn't this Heisenberg. That Heisenberg was Walter White, and the reason why he was called Walter White is because he came up with this thing called the uncertainty principle, also known as the Heisenberg uncertainty principle. And what he said is that you cannot know the momentum and the position of a electron at the same time. And some people actually switch out the word momentum with the word velocity, which both work. So either one's fine, right? But you cannot know the momentum or the position of an electron at the same time. And the reason why this is because, remember, the reason why we see things visually is because light comes and bounces off the object and goes into our eyes. If that didn't happen, we wouldn't be able to see anything at all. So if you're like looking, you have your eyes, right? I'm going to draw something here. Don't laugh, okay? I think does that look like an eye to you? Yeah, that looks like an eye. And we have an electron right here, right? And so what happens is light, okay? Light comes down and bounces off the electron, and then when it bounces off the electron, it goes into your eye, so you can see it, right? But remember, even though light is really fast, it's not that fast. It's not. I mean, it seems instantaneous to us, but it really isn't, right? Because as soon as that light bounces off of that, it actually deflects the electron and makes it go in a different direction. Which means that even though you saw the light coming from the electron's not even sitting there anymore. It's gone moved now, right? Because it got hit by light to begin with. So one of the jokes I always use to remind me of this principle is this joke here. So you're driving down the highway and you get pulled over by a police officer, right? And then the police officer says, "Sir, you're going 80 miles per hour." And then so you say, "Oh, dang. But then now I don't know where I am." Get it? Because Heisenberg says that you don't know your position or your velocity at the same time. And then the police officer says you were going this speed, and then you're like, "Damn. Now I don't know where I am." Right? Get it? That's going to help you later, I promise. So that takes us into quantum mechanics, right? And quantum mechanics was pioneered by a guy named Erwin Schrödinger. And actually, let me take myself off the screen here so you can see the whole thing here. 1 second. Right, okay, there we go. And so quantum mechanics really is what we use, right, mathematically. It was developed a mathematical treatment for determining both the wave and the particle nature of matter, or electron, right? And so this came to be known as a field known as quantum mechanics. And so quantum mechanics is like, always the in thing right now, right? Because we have quantum computing and we have quantum mania, and that kind of stuff. And really all quantum mechanics is trying to do is that it's trying to determine what the most likely place an electron might be, right? And so if you look at this little picture right here, remember that we had for the Bohr model, right, we had the nucleus with the proton in it for hydrogen, and then we had an energy orbital, right, electron orbital around it, and another electron orbital around it. I mean, those are not going to be used. Oh, dang. I messed up my circle. I'm going to have to fix that. But that, let's see here, back to pen. And then, the bigger the atom, the more orbitals it has, but hydrogen only has like one because it only needs to have 2 electrons to be happy anyway. And so the Bohr model showed that's where the electron might be. And that was actually based on the emission spectra, right? And so here in the more of the Schrodinger model, right? Things aren't actually in orbitals, but they're in these things called electron clouds. Electron clouds, right? And then where the cloud is the most dense, right, is the highest probability that there might be an electron there, right? Which is actually interesting because after everything was said and done, they went through and they calculated it with their hydrogen atom, and they found that uh, since Bohr used the line emission spectra, he was actually able to put the line or the energy level uh, at the most probable place that an electron might be based on the quantum mechanical calculations. So that was pretty cool. And so when we solve, there's this thing called the Schrodinger wave equation, right? The Schrodinger wave equation is a very simple equation actually. It's hard for me to draw it because it's a Greek letter that's like weird. It's psi, I think, but I think it's like this. It almost looks like a trident, like that, and then E, like that. So that's the Schrodinger equation, right? And the Schrodinger equation looks very simple, but it's actually very complicated once you try to start solving for it. When you solve for it, what you get is a wave function, right? And the wave function tells you where the most probable location for an electron is. So again, here at the first energy level, right, we have this like electron cloud, and where it's most dense is where the electron might be, most probably will be, right? I'm not going to expand the Schrodinger equation for you, but if you want, you can always take my more advanced class where we talk about quantum mechanics, right? And we do what we call computational chemistry to quantum. Sorry, let me say that again. We do computational chemistry to solve the Schrodinger equation or quantum mechanics, right? All right, so that's going to end this first part of the electronic properties lecture. Stay tuned for the second part where we go through the different types of quantum numbers, the orbitals, and then also the periodic trends. Thanks.